Hello, this is another IGCSE chemistry tutorial, and this is the second part of energetics, which is in Unit 3, which is physical chemistry of your syllabus. And today we'll be talking about enthalpy change. We explored endothermic and exothermic reactions, so pretty much the basics last time, and now we'll be moving into enthalpy change, which is another unit that many students seem to have a bit of trouble with. So let's start. First, let's look at the definition, okay? The definition is actually quite simple. So enthalpy change is simply the energy put in, or given out of a chemical reaction per number of moles. Okay? Let's put this per number of moles aside for a moment and just focus on the energy change, okay? So when we have energy put into the system, of course the reaction is going to be endothermic, and when it's given out, it's going to be exothermic. And actually there is an equation that you can use to find out exactly how much energy is being transferred, okay? And this is one that you need to remember, and it's logical, so I reckon it's not going to be as hard to learn it off by heart, but it's a very important one. So we have Q equals mc delta T. Of course, m multiplies C and multiplies delta T. Q is, well, simply it's the energy being transferred. M, as you have seen it before in chemistry or physics or biology, whatever, is the mass experiencing the energy change. C is a quality called the specific heat capacity. This sounds reasonably complicated, but actually it has a pretty simple definition as well. It's the energy required to raise a given mass of something by 1 degree Celsius. Let's say rise the energy needed to cause 1 gram of water rise in temperature by 1 degree Celsius, and this is why the units are joules per gram per degree Celsius. And of course the grams here is usually sort of simplified in IGCSE chemistry, because, for example, not many questions will represent water being used as 100 grams. It will represent it as 100 centimeters cubed. But in this case, for water at least, 1 centimeter cubed, which is 1 milliliter, equals 1 gram. So we can make this transfer is quite valid. It's not so valid when we're looking at something like hydrochloric acid or another acid, sulfuric acid, whatever. But it's a generalization that we can make in IGCSE chemistry, and that's good. And finally, delta T is simply the change in temperature, meaning. Okay. So this is an equation again that you need to take care of and learn, because it's a vital one. And then we need to bring in this number of moles into the equation, because if in the industry, let's say, or in chemistry in general, you need to know how much energy is released or needs to be put into the system for 1 mole of the reactants. That's a ratio that is very important for chemists. So to find the enthalpy overall, which the sign for enthalpy is delta H, change in enthalpy. When you see this delta, it usually has to do with some change. And here is change in temperature, here is change in enthalpy. So change in enthalpy equals Q, which is the energy transfer, the energy put in or given out of the system, divided by the number of moles. So you can rewrite this to represent the whole story as mc delta T over number of moles. Now let's move on to a more sort of visual representation of what I just said. Let's say, for example, you were asked to draw diagrams to represent the changes in energy during a chemical reaction. We'll have the grids, we'll have time as the reaction proceeds on the x-axis, and energy in kilojoules of the system, of course. So you can remember, energetics, we're always looking at energy changes from the perspective of the system, and we'll have the same sort of thing. It's a pathetic diagram, but it will do the job. Energy in kilojoules and time in seconds for endothermic reactions. Now, before we draw anything, before we put pen to paper, let's actually think this through. Let's actually realize what's going on here, okay? So we've got the reactants. The basic principle of a chemical reaction is that we have the reactants being, well, reacted to form the products. Now, let's think of this from an energy standpoint. This is not quite so simple, but it will be fine. The reactants are, let's say, molecules. We have molecules, okay, of the reactants. They're bonded together. Molecules have bonds. And this bond stores energy in the form of chemical energy. All bonds store some chemical energy. And the same applies for the products. We've got the molecules of the products, and their bonds store chemical energy. Now, in this middle, say, the transition state, we notice that when the reaction is happening, we see an increase in temperature, or a decrease in temperature, depending on the nature of the reaction. So we know that this middle bit must be the heat energy, the thermal energy, heat. So we can think of this model. This is a rather simplified model, I'm not going to lie, but it still will apply to our aim here, which is to draw these diagrams. We have the chemical energy from of the reactants and the bonds of the reactants transferred to heat, transferred to the chemical energy stored in the bonds of the products. Okay, so now let's go back to this to these diagrams. Okay, well, we know that the reactants will have some energy in their bonds. We can't quantify this energy so easily because, well, it's actually quite complicated, but in any case, it's beyond the scope of IGCSE anyway, so we're not interested in that. But let's say they're right here in terms of energy. Okay, and this line is straight because nothing's going on. We just have the total energy stored in the bonds of the reactants. Okay, and I'm going to label that reactants. Then we know that this is an exothermic reaction. So going back to this system here, we know that we've got heat. Let's say there's 100% of heat produced from the breaking down of the bonds of the reactants. Some of this energy, because it's an exothermic reaction, is going to leave the system to go into the surrounding. Let's say 20% leaves and enters the surrounding. So at the end, we can't have as much energy in the bonds, of the reactants as the products. So the energy at the end of the reaction, so the energy stored in the bonds of the products, will be lower than the energy stored in the bonds of the reactants. And I'll label that products. And now we need to complete this middle bit, this part that represents actually the reaction happening. And you'll be maybe tempted to just draw a straight line joining the two, but this is incorrect. What actually happens is that there's a bit of a hill in energy, and from the base of this hill to the top is a quality It's a quantity called the activation energy. And in the name, we can just by looking at the name, we can understand that this is the energy required for the reaction to proceed. Okay, if this energy isn't available, then the reaction won't happen, and we'll just have the reactants staying in their reactant form. Now let's do the same for endothermic reactions, okay? And let's copy this system down again. So we've got chemical into heat into chemical again. In this case, we've got 100% of heat here, okay? But energy is coming into the system from the surroundings because, once again, this is an endothermic reaction. So let's say with respect to the total amount of heat, another 20% enters, okay? So at the end, the chemical energy stored in the bonds of the product will be 120% of the energy that we started with. So let's say if this is 100%, this will be 120%. So some energy has entered, and therefore, if we are to draw the reactants here again, the products will have more energy, will have more chemical energy stored in their bonds, so they're going to end up being at a higher energy level. And I'll label this products. Okay. And once again, don't be tempted to draw this straight line. This is not what happens. There's again this bit of a hill, and again, this energy right here from the reactants to the top of the hill is called the activation energy. Alright? Right. Now, let's go back to enthalpy, because we can also label enthalpy in this case, okay? Remember what we said before? Enthalpy is the change in energy being put in or given out of the system per number of moles. So let's take exothermic reactions as an example, okay? So the change in enthalpy is the change in energy between the reactants and the products. So this, starting from the energy level of the reactants to the products, is the delta H, or the enthalpy change. For the endothermic reaction, it's the same thing. However, in this case, of course, products will be higher than the reactants. This is the delta H, or the enthalpy change. And because we're always looking at the reactions from the perspective of the system, because here in the case where exothermic reaction energy is leaving the system, the sign of delta H will always be negative because the system is losing energy, whilst in the case for endothermic reactions, energy is coming into the system. So always, 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 delta H will have a positive value. Enthalpy energy is coming into the system, so the enthalpy change is positive. And this is all for this tutorial on enthalpy change. This is quite a confusing part of this topic if it's the first time you hear about it. But with a bit of practice and a bit of thinking and reflecting on what actually happens in terms of energy, you'll figure it out. So this is it, and next tutorial will probably be solving a question from the book. So look out for that, and goodbye.